Hello, let's continue with this slide here. So in alkenes electrophilic addition, there should be an I here, apologies. Here we have a reaction between an alkene and H plus H2O. In this case, H plus is acting as a catalyst because you need this as your initiator to attack your nucleophile. H plus itself is quite electrophilic because it does not have any electrons, whereas a double bond is full of electrons. So here you see the mechanism, it picks up the H plus, and after that water goes in, then finally the water picks up the H plus and gets regenerated. So the last step, H2O is acting as a base to remove H plus. You see that this is the one that gets regenerated, so that's why it is a catalyst. So alcohol here is considered an additional product because you see 1 and 2 become 1. So when you have two things become 1, it's an addition reaction. For next part, the very same alkene called 2-methylpropene in the presence of HCl using ether as a solvent, what happens is you get 2-chloro-2-methylpropane, right? So again, in HCl, you have a source of H+, which is your starting initiator of the reaction. Double bond attacks the H+ first, forming the carboxyl ion, and then after the chloride, we go into the carboxyl ion to form this product. Same goes for these reagents. It is very similar, so try to use some analogy and compare and contrast. Now for pen-1-ene, reacting with HCl, our product will be 2-chloropentane. So why? Let's analyze this. We break the pi bond and insert the H on both locations because we are not sure at first. You see, we do this. Then we realize that if the H goes here, the plus charge must be on the other carbon, right? And on the top, we get a secondary carboxyl ion. For the bottom, we get the primary. Obviously, secondary is going to win because primary is not stable. So you won't get this, but only that product, and tada, 2-chloropentane. The next example is very similar. 1-methyl-cyclohexene with HBr. Try out. You got tertiary versus secondary. Tertiary will own this, and that's the only product. 1-bromo, 1-methyl-cyclohexane. Alkynes also undergo electrophilic addition reactions, but the reactivity is substantially less than that of alkene. So let's take a look at this hex 1-ine, 6-carbon terminal alkyne with HBr. First of all, the first pi bond opens up, HBr goes in from the opposite side. You get 2-bromo hex 1-ene, and on further addition of HBr, it goes in one more time, you get 2,2-dibromo hexane. So this again follows what we talked about just now. Now for this part, right, I'm showing the mechanism, like why is this better? Because we have something called the resonance stabilization energy that lowers the energy of the system. This won't be tested for exams or your test because it's just for your own understanding, but it helps you to understand why that's the product that's being formed. For alkenes in general, when you add water, you get alcohol. When you add halogen, you get 1,2-dihalide. When you add a hypohalous acid, halous come from halogen, so it will give a halohydrin. When you add hydrogen, you get alkane. When you add 2 hydroxy group, you get 1,2-diol, 2 alcohol group. When we add a single oxygen, you get a 3-membrane cyclic ether called an epoxide. So from the left, you see that we got 2 reactants like I mentioned before, combining to form one product. So this is the addition reaction. Going backwards, 1 become 2. This is no subtraction, we call it elimination in organic chemistry. THF is a solvent. It is an ether functional group, cyclic member ring, 4 carbon, but it is a 5-member ring. You need 5 atoms to form this ring here. You see this acronym many times in the lecture. THF stands for tetrahydrofuran. Now, to reform my alkene from a haloalkane, we use potassium hydroxide in alcohol solvent. These are the side products. Or we can generate back our alkene from the dehydration of an alcohol using concentrated sulfuric acid. Recall that, right? Your alkene reaction with H+, that's your electrophile, it has something called the regeochemistry involved. That means you will select the particular site that will form the more stable product. Now here, what happens first of all is the double bond, which is electron rich, will so-called attract the atom that wants electrons. So for Br2, we know that Brs in group 7, the halogens, they are electronegative in general, so they want electrons. So what happens is, right, the Br goes in from this way and it gets polarized. Polarized means that, right, the Br that's closer to the double bond becomes delta positive, and the other one that's further away becomes delta negative. The reason is because of repulsion. Electrons, the lone pair pushes this towards this side. It's like here. Electron cloud initially was somewhat symmetrical, but after getting closer, what happens is, right, this is also another big electron cloud. It repels this so that it is bigger on this side and smaller on the other side. So now you see a small positive charge. What happens next is, right, the Br will form a bond with both carbon because Br is big enough. It is in period number 4. Okay, it's big enough to form 2 bonds to form this triangle cyclic ring. But at the same time, you have this ring strain, like the epoxide, like I showed you the other time in cyclopropane. You have ring strain, very bad. So that's why this is quite reactive and it tends to open easily. We call this a bromonium ion because this is now the Br that carries a positive charge. For this case here, our electrophile is a mercury 2+ ion. Undergoes similar attack with the alkene and it forms a 3-member ring. Let's do a comparison of the 3-member rings. Mercurium ion, bromonium ion, oxonium ion. All these are very similar. We can use an E to represent these, E+, because it is electrophilic. So, what is all this about? Basically, we know that this tends to open up, but which way does it open up? Does the E goes to the right side or the E goes to the left hand side? Let's see. If the E goes to the right hand side, we are trying to break this bond here. That means this carbon here I'm pointing to is having a positive charge, which makes it something like a tertiary carbonyl ion. So that's why nucleophile prefers to go in this manner. For the bottom case, if I'm trying to lean my E to the left hand side, that means I'm trying to break this bond here. We are going to get a primary carbonyl ion, which is very unstable, and that's the reason why you don't get this case. So from the top, you continue the attack, you get regeochemistry selectivity. So E goes there, and you goes to the next carbon, and this is the only product. What is the anti-addition? Anti, as you know from the lectures, it means is opposite. Right? So now you have a 5-member cyclopentane. We know that it's pucking in shape, and when you form a 3-member ring, the E either goes above the plane or below the plane. It can't be exactly on the plane because it's not stable due to the ring strain and angle strain. So it's going to choose one side to attack by the nucleophile. Now for the very same manner, we know that if I'm trying to break this, I'm going to get a secondary carbonyl ion. For the bottom, we're going to get a tertiary. So our mind is clear that it's going to take this way and not the top. But the next thing is it from the top or the bottom? Now here we use the 3D geometry and look at the molecule from the side. So this is your 5-member cyclopentane ring. The E points up here. That means the methyl group points down because they try to avoid each other due to steric repulsion. The next step is your nucleophile coming in from the bottom right because you want to avoid this big electron cloud. So we know that's going to attack this carbon here. But is it from here or from the bottom? The answer is it's from the bottom because by this trajectory, it will avoid head-on collision with this electron cloud. So you know repelling head-on is very bad. Like when you go to have a fight with someone head-on, very bad, okay? People get injured. It's scary. So you try to avoid conflicts at all costs. In chemistry, we have some words to describe this attack. Now, people may say it's a top attack, T-O-P, right? That's a boy from Korea. He sings pretty well. Or bottom. But these are not professional words to describe this attack. You should be using suprafacial, which means coming from the upper face, or antarafacial. You know what's a facial, right? You know facial, like the face, alright? So this is what we call suprafacial attack and antarafacial attack. And now you see that, right? The two groups that went into the original reactant, they are on the opposite side, and we call them an anti. So anti-addition. Next, over here, again a similar alkene reacting with H+, you get this carbocation intermediate. Now next reagent here is actually a BH3. BH3, we call it borane, not boring. Borane, okay? Lectures are not that boring. Borane, you see that right here we have an empty orbital because when you draw this out, BH3 is actually trivalent. There's only 6 electrons around the boron. 6 electrons, 1, 2, 3, 4, 5, 6. So B is short of 2. So what happens is it prefers to align itself in this manner and goes up this way. So we analyze, is it that way or is it this way? Now if it's this way, what happens is B is rather big, is from the second period, it will hit the big bulky dimethyl groups here. So it prefers not to have this kind of steric crowding and avoid this. If it's on the other side, it's much better. So it goes in this manner, goes up, form a bond, and you get this. It's an intermediate. This is what we call a syn addition because if you use an alkene in the presence of BH3, right, it must come from the same side. The incoming groups are from the same side. So this stereochemistry, we call it syn addition. Syn, same side.